So we're going to do some integration then. Again, I'm going to try my best to be nice and neat with this. The rules are we just have to do whatever integral, or I need to actually change this to say 700, and then we'll 290 is our first one. We just have to do whatever integral it gives us. 290 is the first one, so 290 is found a little bit further down here. So 290 is, why is it zooming out? 3 to the x over 3 to the x plus 1. Now this one's quite an easy one because the denominator derives to the numerator, except it doesn't quite, right? Because 3 to the x derives to 3 to the x times the natural log of 3, I believe. So I think we just need to divide that by the natural log of 3 and say the answer is log of 3 to the x plus 1, all divided by the natural log of 3, I think, just to get rid of that thing. So yeah, for most of these questions, we'll actually get some paper out and we'll do these properly. But when they're easy, and I think 130 is disappointingly going to be another easy one. But again, the rules are the rules. We just have to do whichever ones it gives us. We can't skip. The rules are the rules. This just integrates, right? It's reverse chain rule. Is it even reverse chain rule? Or, I mean, sure, I guess it is. So that's 3x plus 1 to the power minus 3 over 2. So we add 1 to it to get to minus a half. Divide by minus half, which is the same as times by minus 2, I guess. So is that minus 20? And then, of course, we still need to have that 3, so over 3. Is it over 3? Or is it, yeah, over 3 into 3x plus 1 or to the power minus a half? Something like that. Again, pretty silly one. I should probably put a more reasonable minimum number on here to skip the ones that aren't interesting, but I don't know. 221 is down here somewhere, not too far away. So this one seems okay. So this is sine 2x over 1 plus cos x. So we're immediately obviously thinking about some kind of substitution, some kind of double angle formula with sine 2x, right? So integral of sine 2x. So actually the first one I'm writing down over 1 plus cos x, I think, was the integral dx. Now sine 2x is, of course, 2 cos x sine x. So we're thinking, firstly, is that even helpful, 2 cos x sine x? Because, like, nothing would actually cancel if I wrote that as 2 cos x sine x. Nothing would quite cancel because of the 1 plus cos x on the bottom. So maybe that doesn't end up being too good. So that's kind of disappointing. Maybe it does work. I think it probably does, though, right? If we make that change and then we also substitute u equals cos x, I think this will be the ticket, because we get du equals sine x, or actually should be minus sine x, right? Dx, which means, of course, that dx is du over minus sine x. And the reason that's good, of course, is because when this sine x gets put in there, it's going to cancel with that sine x when this gets put in there. So I think we end up doing something like the integral of minus 2, the 2 being from this one and the minus being from this thing here. And then the signs will cancel, like I said, so it ends up being cos x, which is just u on the top, over 1 plus u on the bottom, du. And I think that's all cancelled properly. So that's good. That's good progress. How do we integrate u over 1 plus u? Well, the most obvious thing to do, I guess, is make a second substitution of m equals 1 plus u. That's a linear substitution, so there's no need to worry about anything going on there. We just get m minus 1 over m dm into the integral of minus 2. And then this, of course, we can cut in half to be 1 minus 1 over m, which integrates to m minus log of m, log of m. And then I guess we put both substitutions back, so that's 1 plus u minus log of 1 plus u. And then, of course, that's put in the cos, so it's going to be 1 plus cos x minus log of 1 plus cos x. Cool, so that's that done. I'll move this out of the way, ready for the next one, hopefully, which we'll also be doing. So we've got, so the next one needs to be given here. It's 523, so that's a nice big number, so hopefully this will be interesting. 523 is further down than that, a little bit up. 523. 523 is here. There we are. E to the x sine of x. Oh, so this is an absolute classic, right? Absolute banger. I think this is one of those ones that if you've done enough integrating, you just look at this and you immediately know how to do it. Now, I'm wondering while I'm writing this whether to bust out some integration by imagination, which I think was exactly what I used. I think this was exactly what I used that on. And I'm desperately trying to remember exactly how to do integration by imagination. Because, of course, the usual way of doing this question is just to do integral by parts twice, right? Because if you call this I, what's going to happen is you're going to integrate by parts. You can integrate the e to the x as many times as you want. So that's just going to be e to the x, leave the sign of x alone. So this will still be I equals. And then we're going to take away the integral of, again, integrate e to the x, which is still e to the x, and differentiate the sign of x, which is a cos of x. And now this doesn't look like it's improved the situation. But what you can, of course, do now is you can do the whole thing again, and you get e to the x sine of x on its own out there, minus, and then big bracket, do more parts here. I'll try and write this nice and small. E to the x cos of x, just leaving that one alone, minus the integral of e to the x integrates, and then cos of x differentiates to make minus sine x. This ends up being a plus here, sine x dx. But of course, this thing here is just I. So we get I minus I over there, so that's a 2I equals e to the x sine x. Sorry, my hand, I'm left-handed, so I keep smudging the page, which is what all these dots are, I think. Cos x dx, and then we just divide by 2 to get I equals. Now, integration by imagination, how do we do that again? Is it something like saying e to the ix equals cos of x plus I sine of x? And then you say, therefore, that sine x is the imaginary part of, oh, what do you even do? I can't remember. The imaginary part of this? No, the imaginary part of this? Yeah, and then you have like, then this ends up being the imaginary part of you bring the imaginary part out. I can't be bothered to do it. Watch my video. It's a good tease. That's what proper YouTubers do, isn't it? They don't do it in this video. They tease the fact that there's another video in the world called Integration by Imagination, and then they farm the views there by just saying that you should go watch it. You should go watch it. 137. I haven't done it in. I mean, I haven't done it since I did that video, which is why my memory was hazy on that. 137 is all the way up here. I know I'm a fake mathematician. I can't really do the stuff that I do. Okay, this looks immediately cool because e to the x plus e to the minus x is, I believe, is that 2 cos x? And now we're wondering whether that's actually going to be helpful or whether that's going to make the situation much, much worse. It's probably going to make the situation much worse, right? Let's put this down first. So integral of 1 over e to the x plus e to the minus x plus 2. So it's not an easy integral, or not easy integral to remember, I should say, plus e to the minus x plus 2 dx. I'm probably just going to double check that I wrote that down right, because it's really annoying when you don't. And yeah, I think I can see that just about right. Okay, so yeah, as I was saying, e to the x plus e to the minus x is 2 cos of x. I think that makes this worse, because you could factorize out of 2 and leave yourself 2 cos of x plus 1, but I don't. Oh, I guess then you could times it by cos x minus 1 over cos x minus 1, and maybe get some work done. I think this is massively overcomplicating it. I think u equals e to the x is the way to go here. So du is e to the x dx. E to the x itself is u, so that means du over u equals dx, which makes this the integral of 1 over u. Now, e to the minus x is 1 over u, or u to the minus 1, plus 2, and then we're timesing that by du over u. So if we expand these brackets down at the bottom here, we end up with u squared plus 1 plus 2u, and here's the ticket, right? Because when you have, sorry, that wasn't very neat. I've gone back on my promise already. This is a quadratic on the bottom. So this is the integral of 1 over u plus, oh, it happens to be something squared itself, u plus 1 all squared, which makes it borderline easier, right? Usually when you have quadratics on the bottom of a fraction like that, you want to complete the square, because then you can get some arctans or whatever the integral would be. But if it completes to factorize perfectly like this, then of course this just integrates straight up to u minus 1 to the minus 1 with a minus 1 in front maybe. And then we put the u back, and we'll be done. So yeah, kind of cool question there. What I was talking about with those coshes is, as I suspected, I think way overboard. I don't think that's necessary in any way. Although it would have been quite a cool way of doing it, I think. So if you want to pause the video here and have a go doing it like that, I was suggesting, I think, did I suggest put the cosh in and then times by 1 minus cos x, or cos x minus 1 or something? I think it has hope of working, but I think it's a massively overcomplicated way of doing it. Anyway, here we have cos 3x over sine squared 3x. So I'm immediately nervous because I don't remember my triple angle formulas at all, and I do not want to sit here and derive them. So if it comes to that, I'm probably just going to not do this integral. That I think that was a squared, if I'm honest, but I will double check because, of course, always good to double check. Cosh 3x over sine squared 3x. Yeah, cool. So we're immediately thinking, of course, that cosh over sine is koth. Is it koth? Is that how you say it? So I guess we could write this. Let me just get rid of these marks that keep coming up when I try and change the page. So we could immediately write this as like the integral of, I guess it's koth 3x. That's using the cosh and one of the sinches, and then of course we'd have cosech left over because there'd be one more shine on the bottom. So I guess we could write it like this. Now I'm thinking regular trig here because I think that sec derives to sec tan. Just writing some notes up here, which means of course that sec tan integrates to sec. And I know that's true. So I think that means that cosec becomes cosec cot with a minus, if I remember correctly. I think one of them has a minus, and it must be that one because it's not the other one. So that integrates backwards. And now I'm going to assume that the same is true for hyperbolics. So I'm going to assume that cosec coth integrates to cosec. And the 3, I'm going to assume, just means I need to put a third here. And I think I need a minus to make that all balance out. So I think, I don't know, that might be completely wrong, but like if I was in the middle of integration B, that's what I would put, and I would just hope that I was right, because actually dealing with this properly seems like it's going to take much more time. And you know, I'm vaguely confident-ish that that's probably good enough logic. It usually works, so let's go with it. 1, 2, 1. We've actually spent way more time on this than I thought we did. Sorry, I thought we were only like 5 minutes in. Time's flew by. 1, 2, 1. Let's just do a couple more. 1, 2, 1's probably not going to be. Oh my gosh, it's probably not going to be too tricky. What is wrong with this? 1, 2, 1. Can we do this very quickly? So okay, we break this in half. We get tan of x plus, or tan over cos is, well, it's sine over cos. That's sine times cos to the minus 2. Okay, so the first half, when we break this fraction into 2 pieces, is just tan. That integrates to log sec, I believe. Maybe I should do this one properly because there's a bit of writing down to do for this one. So I'll do this one properly, just to make it clear what I'm doing, because I think a bunch of the results that I'm kind of about to quote maybe not so obvious to lots of us. So sine x plus tan x over cos x, I believe it was. So what I was saying was I'm going to break this up in half here, and I'm going to pretend that this is the integral of sine x over cos x, which is of course just tan x. So we've got the integral of tan x, and then separately we've got a second integral to do, which is tan over cos. Now tan is sine over cos, so sine over cos is sine over cos squared, which I could write as sine of x cos of x to the minus 2 dx. Okay, there should also be a dx here. Now this one over here, that's actually quite easy to integrate, despite the fact it looks quite complicated, because it's just f dash of x sitting next to f of x. So I think this integrates to minus cos to the minus 1, although actually, because cos differentiates to minus sine, I think that minus cancels and we just end up with this here. Think doing chain rule here, you put the minus 1 down, make it a minus 2, cos differentiates to minus sine, that cancels that minus, but also gives you that sine, so perfect. Now tan is sine over cos. That is a derivative sitting over the top of its own function, so that integrates to log of cos, but with a minus because cos differentiates to minus sine, so it's minus log cos. But of course, minus log cos, the more usual way of saying that is you put this minus at the top here and put a minus 1, but cos to the minus 1 is sec, so it's actually log of sec x. And then plus cos x to the minus 1 is the other bit. Cool. Thank you so much for watching, and I'll see you next time.